Good morning to all.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning. Sorry
Morning,
for
sir.
good morning. I have late due to some file problem, some word problem. I got it. Okay, now it's fine. Today I am going to start the numerical problems on binary fluid systems. Again, last class I explained the properties as well as the process. So now I'm going to explain the solutions. That's especially for applied to binary fluid system. These solutions can be categorized into two groups. One is um, tab using tables you can solve the problems. The properties can be picked either from the tables or from the graph. Same like Steam also. Steam analytical solutions, how you are solving the properties you are taking from the Steam tables and you are substituting in the formula and you are solving the efficiency or output from the Steam power plant. Similarly, here also, the binary fluid system can be solved analytically using formula. To substitute the properties in formula, we need the values of the properties that you can refer the tables. These tables actually it's not available in the books or literature. I prepared my own and it's the same I'm presenting here. So it's easy to use because once you are referring the graph, it's difficult to take the exact value of the property. Some error may come, even though that is easy. Using graphs it is easy, but exact solutions you can't get. So exact solution you can get by this analytical approach, even though it is tedious compared to graphical, but it will give the accurate value. And the graphical solution you may use the enthalpy, specific enthalpy concentration chart. Using scale pencil, you can identify the states, draw the lines, and you can get the solutions. Okay, now I am showing these graphs, a typical pressure of 1 bar, because each table has been prepared at constant pressure. The pressure is constant. Even graphs also see a loop, a family of the liquid, auxiliary, and saturated vapor. Three curves together consigned to a one particular pressure. Similarly, this one table is related to one pressure only, at constant pressure. This ammonia water vapor property system at 1 bar under saturated and wet condition, under saturated and wet conditions. So this is, I can say, the liquid vapor mixer. At this liquid vapor mixer, we may refer what properties we can see: the specific volume, enthalpy, and S is entropy. Concentration is small letters. I will open the PDF files. I will show. And the concentration of liquid, concentration of vapor, and temperature. See, the temperature is variable in liquid vapor mixer. Once you are keep on adding the heat, the variable temperature phase change takes place at the variable temperature. And its ammonia concentration, the mass fraction, that is x is changing from 0 to 1. This first column indicates that x is equal 0, indicates it's a completely the H2O, and the last column x is equal to 1 indicates that's a complete NH3. And another details you can see, this is the dryness fraction. Okay, 1 minute, I will enlarge. Let me open another file. Are you seeing this graph?
Yes, sir.
I think the size may be somewhat better compared to the. Are you able to see the values here? I am reading ammonia concentration, mass fraction X.
Yes, sir.
These letters are visible. Okay, fine. So as I told, these properties here in this annexure I gave this book, it's grouped into saturated liquid properties. After saturated liquid properties and 1 minute, I will show. Saturated vapor properties. These are saturated vapor properties. Second category is the saturated vapor properties, and third one is ammonia water liquid vapor mixture properties. So I can group into three: the liquid, vapor, and third is liquid vapor mixture. So these are the tables, same like steam tables, but this is concentration is added as a extra property. Followed by chart, enthalpy concentration chart. Okay, first one by one, let me explain one by one. The first one is liquid properties. How to read the liquid properties. See the first column is pressure is changing 0.15, 0.2, and is maybe in case of refrigeration system up to 20 bar is enough. In case power plant, it's more than 20 bar. That means sometimes the turbine will operate from 50 bar, 60 bar. That's why the properties has been extended beyond 20 bar. It's given up to 54 bar here. Okay. So up to 54 bar, you can pick the properties from the tables. It may be region may be liquid, vapor, or liquid vapor mixture. In this liquid, X is changing from X to 1. If you are referring, let us say the pressure is 0.5 bar, what you can read? You may read the temperature. This temperature is changing from X is equal 0 to X is equal to 1. Okay. 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then for last is a X is equal to 1. That is variable temperature. See, the temperature is changing. And what about next one? The next row is a specific volume, specific enthalpy, specific entropy. Okay, fine. This you can take directly from the tables. And I want to ask you, what is the name that at x is equal to 0, at 0.5 bar, the temperature is 81.34 degrees centigrade. What is the name of this temperature? Anybody? At x is equal to 0, the temperature of the liquid is 81.34. What is the another name of this temperature?
Saturated water.
No, it's a
Saturated liquid, sir.
yes, it's liquid. Okay, the technical name as per the binary,
Saturated liquid.
not saturated liquid. That is water term, and since it is completely saturated liquid, it is related to complete water. This is saturated point. And once you are going to ammonia side, what is the, how this temperature is changing? That is now 81.34, 50, 29, 11, minus 5, minus 19. How it is changing? Last it is minus 46.35.
Decreasing.
Okay, I will open the atmosphere pressure. Then you may be familiar, atmosphere pressure is familiar. You will get some idea. Yeah, atmosphere pressure I can't pick here. 1 bar is there. Okay, maybe 1 bar is close to atmosphere pressure. Maybe you can see 99.38 degrees centigrade means that is close to 100 degrees centigrade. Now see x is equal to 99.38 at 1 bar. What is the meaning of this 99.38 at 1 bar?
Boiling point of liquid. Water.
Yeah. This is the boiling point of water at, because that is x is equal to 0. and its a boiling point of water is 100 degrees centigrade at 1.01325 bar. Since it is slightly less, that's why the boiling point is also less than 100 degrees centigrade. And if you refer the same atmosphere pressure, approximately 1 bar, and coming to the ammonia, the pure ammonia, what is this temperature?
Boiling point of ammonia.
The boiling point of ammonia.
Yeah, minus 33.67 degrees centigrade. So this boiling point, actually pure substance, that's why you are saying this is a very specific. If it is a pure substance, means there is no difference between the bubble point and dew point. Both are same, both are joining. That's why you are seeing like I loop in charts, concentration chart. But if it is mixture, let us say from 0.1 after 0, I am saying after 0, that means as per this table from 0.1 to 0.9, point, do you what do you could you give the name for these temperatures? It's changing from 68 to minus 31. What is the specific name of the as per the binary fluid as per our discussion? It is a liquid. All the
Liquidus line. Liquidus line. Means
uh-huh.
its locus will give us the liquidus line.
Liquidus line,
Saturated
and
liquid.
with reference to the temperature, since this is a temperature row, this is called as bubble point temperature. Got my point? These temperatures are bubble point temperature. Bubble point temperature refers to the starting of the phase change. As the saturated liquid is refers to the starting of the phase change. That's why I can call these temperatures as a bubble point temperature. If I am referring the vapor temperature, in case if the same table is designed for the vapor, I can call this temperature as dew point temperature. Have you got my point?
Yes, sir.
If it is related to the liquid, that's in starting of the phase change, you may call that as bubble point temperature, BPT. And if it is related to the vapor where phase change is completed, that is called as dew point temperature, DPT, dew point temperature. Okay, now you are clear about this saturated liquid properties with reference to the change in the concentration and change in the pressure. Okay, coming to the next one, saturated vapor. Okay, 1 minute, it's going. Yeah. So this is a saturated vapor. The pressure is started from 0.15 bar to again up maybe up to 50 bar. It is given, and again let I will select the 1 bar because that is also again close to atmospheric pressure. At 1 bar, T is equal to 99.85. This temperature is refers to boiling point of water at atmospheric conditions. That's I will agree. And what about the 1 bar? This is minus 30.71. This is also refers to the boiling point H2O at this temperature at this pressure. A small error is coming because that's a rounding error actually speaking. Okay, coming to the x is equal 0.1 to x is equal 0.9 at 1 bar. See here it's changing 96.59, 93, 89. It's decreasing and it's going to 50.8193 degrees centigrade at 0.9 concentration at 1 bar. Now, could you give the name for these temperatures? This is they are refers to the saturated vapor conditions. That means where phase change is completed. What is the name of this temperature? Exclude the pure substance like x is equal to 0 and x is equal to 1 is a pure substance. That's why that's means a single fluid. Leave it. For the mixture,
Dew point temperature.
this is the dew point temperature. Okay, now I covered the extreme ends like the fully liquid properties I covered and fully vapor also it is covered. Now the question is If the state is between these two curves, that means above the saturated liquid and below the saturated vapor, how to read the properties? Then you may refer, first of all, before going to the table, how to conclude whether the region is liquid vapor mixture. That means we have to compare the temperature with both bubble point temperature and dew point temperature. If the temperature of mixture is lying between bubble point temperature and dew point temperature, immediately you can commit yes, that is lying between liquid and vapor. That means liquid vapor mixture. So immediately refer this table, liquid vapor mixture table. Yeah, yes, yes. Here it's given from point 1, point 2, point 3 onwards. So ammonia, water, liquid vapor mixture properties. Sorry. This is at 3 bar. It's starting from 3 bar. It is given. Yeah, 3 bar, 4 bar, 5 bar. It's so on. It's given like this. The thing is here, sometimes if the given pressure is not matching, sometimes you need to do the interpolation. The two direction interpolation, maybe row wise interpolation and column wise interpolation we have. Okay, first let me take the example of 3 bar. With the 3 bar, axis changing from point 1 to point 9. Axis changing from point 1 to point 9, and we excluded x is equal to 0 and x is equal to 1 because those properties are already covered in the earlier tables. That means liquid tables as well as these vapor tables. And between x is equal to 1 and x is equal to 9, the liquid vapor mixture has been given. Okay, if the pressure is 3 bar, if the pressure is 3 bar and theta is actually this is phi. I will change the notations. This is I prepared long back. I will update some of the nomenclature. The dryness fraction is changing from 0.1 to 0.9. Yeah, 0.9. The dryness fraction is taken. If the dryness fraction is equal to 0, that's completely the liquid, and dryness fraction is equal to 1, that is also completely vapor. That also has been excluded here. So between the 0 and 1, for given values of 0.1 to 0.9, and dryness fraction 0. Also 0.1 to 0.9, what we are doing, we are going to calculate the we are going to pick the properties of this liquid vapor mixture. For example, if the pressure is 3 bar and dryness fraction is 0.9, what type of properties we can see? And concentration is 0.5. See this column. T temperature is 49.74. Specific volume is 0.17, and enthalpy, specific enthalpy of the mixture 459.85, and the specific entropy 2.1, and concentration, the liquid concentration is 0.39, vapor concentration is 0.98, and liquid enthalpy, sorry, this is a liquid enthalpy, and next line is a vapor enthalpy. Yes, up to vapor enthalpy you can see temperature, volume, specific entropy, liquid and concentration, vapor concentration, liquid enthalpy, and vapor enthalpy. So this combination of these liquid properties, vapor properties, and liquid vapor properties, you can find exactly, you can find the properties using the tables. Okay, or in case if you are using charts, in case you are using chart, actually the chart is in the landscape. 1 minute, I will change the direction. Okay, are you clear about this drawing? Is it visible?
Yes,
Yes,
sir.
sir.
Okay. In case you are using chart, tables means you have to see according to the region, liquid region, vapor region, or liquid vapor mixture. Okay. Now coming to this chart, if it is a liquid, these all curves are refers to the saturated liquid. Okay. How you can refer the properties here? The x-axis is the concentration, x-axis is the concentration, and y-axis is the specific enthalpy. You can read the enthalpy, liquid enthalpy. For this case, liquid enthalpy. And apart from this, because the properties generally it is we can read by ptx coordinates, ptx coordinates. Okay, where is the pressure? This curves refers to the pressure. How you are seeing this? This 0.2, zero point 0.4, these are the related to the pressure. The last curve, the upper curve shows the high pressure, that is a 20 bar. So 0.2 bar to 20 bar, the pressure has been changed. Okay, you can refer the pressure and the concentration. Now, if I am seeing this, let us say the zero point 0.5 is the concentration, and the pressure is 4 bar. I have to stop here. Then what is the dew point temperature? Since it is a saturated liquid, if I am giving the inputs like pressure and concentration, you can read the bubble point temperature. Liquid means this bubble point. What is the bubble point temperature? Anybody could you say? It is between 20 and 40 degrees centigrade. It is between 20 and 40 degrees centigrade. If it is 0 0.5 and 4 bar, this is a 4 bar, approximately between 20 and 40 degrees centigrade. Very clear? Zero point 0.2, zero point 0.4, zero point 0.8. Okay, at most 1 bar. 1 bar. What is the what temperature you are seeing here? 100 degrees. Are you seeing 100 degrees centigrade here?
Yes, sir.
It's slightly less than 100, I mean 99, 98 something. 100 degrees centigrade, because this is a pure water. And if I am referring the 1 bar, see here, what is this temperature? Okay, I will adjust. 1 bar. What is this temperature? You can see the blue color lines, that is temperature lines.
So close
Minus
to
40,
minus 40.
minus
Minus
40
50.
and close to minus 40, but towards minus 20.
Yes.
Towards minus 20. It's minus 34, minus 35 around at atmospheric conditions, I am saying. So you are able to define bubble point temperature at given pressure and temperature.
Concentration.
Sorry, at given pressure and concentration. At given pressure and concentration, you are able to read the temperature. This is for the completely liquid phase only. But if it is a liquid and vapor, we can't solve like this. We can't solve directly like this. This is a direct method. Since it is a pure liquid, 100% liquid, directly you are able to read the temperature. But if it is a liquid vapor mixture, as I explained in earlier, we can't read the temperature directly. We have to use some iterative method like identification of the temperature or isotherm. Okay, using this either chart solution or maybe tables. Okay, coming to the same, this is a vapor, this is auxiliary curve. This auxiliary curve is used to to solve the liquid vapor mixture, and whereas this last curve shows the property for the saturated vapor conditions. So the combination of this liquid, auxiliary and vapor gives one loop at one particular pressure. Now pressure has been changed from 0 point to 20 bar. That's why you are able to see a family of curves that I'm calling this as enthalpy concentration chart. So according to your convenience, either you can refer the tables or this chart, that's enthalpy concentration chart. Okay, see this process, separation process. I explained the separation process in this earlier explanation. For example, to find the separation temperature, liquid concentration, solution concentration, and solution enthalpy in a separator located after the vapor generator, that's boiler, with the following data. The required dryness fraction is 30% at the pressure of 13 bar, and the ammonia concentration in the vapor at the exit of separator is 0.88. What is the given data here? We have to this here we have to solve the separation process. Mostly solution means that's exit condition we have to find. What the meaning of process solution? Process solution means the exit condition is unknown actually at the exit of at the outlet of separator. What is the conditions, the properties conditions? So here we are solving this process by finding the exit condition. What the information given here? The dryness fraction is 30%. What is the meaning of this dryness fraction? You know, separation means it's liquid and vapor mixture. Okay, liquid is 70% and the vapor is 30%. Okay, dryness means the vapor is 30%. The balance is a liquid. That's a 70% is a liquid. That's fine. You got the phi is equal to 0.3. That's a vapor fraction or the dryness fraction. And pressure. All the separation process takes place at the constant pressure. It is a 13 bar. At 13 bar, liquid and vapor has been separated. And the ammonia concentration in vapor at the exit of separator is given. Actually, the problem may be given in a straight away or maybe in a tricky conditions. Then in project means mostly the constraints will be there. Constraints may be the inlet condition or outlet conditions. Here, according to the plant, I think so, this constraint has been given. After the separation, the required vapor concentration is 0.88. The required vapor concentration is that is XV. XV refers to vapor concentration, XL refers to the liquid concentration. So XV is referred here 0.88 and solve the problem. What we have to solve here, at the inlet of separator, the concentration is required and liquid concentration is also unknown. And also temperature is, we don't know temperature also. Okay. Now, could you think about the solution? How to start the solution here?
So we can mark the exit point 0.88 and 13 bar
Yes,
on the
sir.
top.
Yes, it's correct. Just now we had discussion for liquid, not for vapor. See, in the liquid chart I showed for given pressure and concentration, we are able to read the temperature. Here also, but this is vapor for given pressure and concentration. 13 bar and 88 the concentration. There is a one particular temperature. You know, there is a one particular temperature that is also called as a dew point temperature. If you are able to identify the temperature, that is a separation temperature. Because the same temperature you can apply for the liquid and the same temperature also you can apply for the mixer, because that is the isotherm. Isotherm is passing the liquid, the vapor, and the mixer. There are two points. I will show the points. Actually, process is not shown here. Okay, you may see the points here. The one is before separation. State one is the before separation, and state two is liquid after separation. This is the liquid. That's saturated liquid. That's why you can see a blue color curve here. And state 3 is a red color it is showing. State 3 is a completely the vapor. So now 3 has been defined completely. The state 3 has been defined completely. So it is 88%. If I am drawing a vertical line here in the chart, 88%, and 13 bar, you may see here the pressures 13 bar. Actually this graph I took for 50 up to 50 bar. what I showed the figure that is given up to 20 bar, that means more clarity you can get it. If I'm drawing up to 100 bar, the more congested curves you can see. The of course here 13 bar point I'm showing as 3. So easily you can locate point 3. Easily you can locate point 3. Now see this explanation. The graphical solution has been explained for this solution of the separation process. A scale and pencil can be used with enthalpy concentration chart for the graphical solutions. For graphical solution, locate a state 3. Yes, we can start the state 3. It's easy to locate the state 3 because we know the condition. We know the pressure and we know the concentration. The vapor curve and 0.88 concentration and 13 bar. Draw a horizontal line. Actually, this is the reverse position. Earlier, I explained I started from the liquid and vertical line till auxiliary and followed by horizontal line till the vapor line. But since we know the vapor state instead of liquid state, we are starting from the vapor. Draw a horizontal line till auxiliary curve. Till the auxiliary curve, I think it's magenta, the pink color you can see here. Till the auxiliary curve and extend to a vertical line from this intersection. Once you are reaching 13 bar, this is a 13 bar curve, you have to stop here and draw a vertical line. From here onwards, draw a vertical line. Where you have to stop in the liquid, here also you can see the 13 bar curves. The pressure curves we are seeing here, at 13 bar you have to stop here. So you are able to draw a right angle triangle. Okay, this is a horizontal line and vertical line, there is a right angle triangle will come. After that, the vertical line meets the saturated liquid line at liquid concentration at state 2. That's liquid, both liquid concentration and temperature can be read as, since you can see the temperature lines here I showed in the Zoom earlier slides, you can refer the temperature curves here. So this liquid point indicates the concentration of the liquid and also the temperature of the liquid. So the temperature of the liquid is here 117 degrees centigrade. Concentration of liquid 0. 0. This is refers to our figure. I don't know exactly. It's showing 0.28. It is 0.28 and temperature is 117. From the lever rule, we can find the mass. After that, you have to join this point. Join 2 and 3. You will get a straight line. You will get a straight line. But what we are able to read here, you are able to read the liquid concentration 0.28 and vapor concentration already it is given 0.88 and temperature of process also 117 degree. Here temperature goes 117 degrees centigrade. What is unknown here? The lever rule we have to solve to get the unknowns here. The lever rule, from the lever rule, are locating the point with length inversely proportional to the dryness fraction. What is the dryness fraction given here? 30%. Dryness fraction is 30%. Using scale, if you take the total length of this line in millimeters, that line you may divide into 30% and 70%. Maybe you may use the calculator. If you have, let us say 100 millimeters you are getting, for example I am saying 100 millimeter you are getting means 30 millimeter one side, 70 millimeter and another side. Which side 30 millimeter, 70 millimeters, where how to divide as per the lever rule? May I know?
Vapor side 30%.
Vapor side, that no, it's opposite side, lever rule is opposite.
Opposite side, yes, sir.
This is a vapor, State 3 refers to the vapor. Opposite side 30% you have to maintain. Got my point? The length 1, 2 is a 30% of the total length. Automatically the vapor side length becomes the 70% of the total length. This is as per the lever rule I am saying. Opposite side length is proportional to the concerned mass. This mass of the vapor is proportional to the length towards this liquid, and mass of the liquid is proportional to the length towards the vapor. I think that you are clear, I think so, as per our earlier discussion. Now, from the lever rule, or locating the point with the length inversely proportional to the dryness fraction, a point 1 can be solved. After locating the point 1, you may read the concentration, this mixture concentration. Your mixture concentration is showing 0.46. Now you have all the three concentration. The mixture concentration is 0.46, liquid concentration is 0.28, and vapor concentration is given as 0.88. So these concentrations, based on this concentration, you can also solve the other values like enthalpies or etc. Enthalpies directly you can read from the graphical solution. HL, H, HV. Enthalpy of the liquid, enthalpy of the vapor, and enthalpy of the mixture. Without using any formula, straight away you may read this all the enthalpies. The solution enthalpy from the graph is 770 kilojoules per kg. But also you may refer the liquid enthalpy as well as this vapor enthalpy. So the figure shows the solutions for the separation process on enthalpy concentration chart. For mass calculation, at least one mass they have to supply. That means if they are giving the mixer mass, let us say 1 kg, accordingly we can split into 30-70%, but there is no any mass information. That's why we are not able to find this mass, liquid mass, vapor mass, or the mixer mass. If in case if the mass information is also supplied in the problem, we can also extend not only for concentration solution and enthalpy solution, we can also extend to the mass solutions, means ml, mv, and m. No need to extend for exergy because this explanation is limited to energy solution only. That's why the entropy and exergy is not included here, because that's not our scope. Of course, you can do that exergy evaluation also based on our earlier explanation, what we studied, the elective, the exergy analysis of thermal system and energy systems. The same knowledge you can apply, but since that objective is not included in this poly generation, that you may do according to your interest. Okay, are you clear about this graphical solution?
Yes, sir.
Okay. I will share the material. Sorry, actually, I'm preparing some files, PDF files. I will finish. After finishing, I will share. My suggestion is take the print for each and every question. Take a separate print. For example, after finishing the separation process, keep it as a record, like a notes. Don't erase and don't do the second problem in the same graph. Are you getting my point? Because this is a Xerox copy. Once you are taking the Xerox copy or printout, erasing means even the black colors lines also will erase. But that's not the issue. You may use a separate curves for practice and internal examinations as well as the end examinations. That's why you can take as many, maybe 10 to 15 copies, so that you can practice at home. Okay, first we are identifying this point in the vapor 88% and 13 bar, and draw a horizontal line till the 13 bar. From that point onwards, draw a vertical line till again the 13 bar. 13 bar. This goes. You may get one cutting point. Join this liquid and the vapor. Join this liquid and the vapor, and using scale, take the total length and divide this length into 30%, 70%. Then you can locate the point between the liquid and the vapor. That point indicates the mixer concentration, mixer enthalpy. Apart from this mixer, the liquid enthalpy concentration, liquid enthalpy, vapor concentration, vapor enthalpy. That's all. I think this is clear. Graphical solution is easy also. because you didn't use any single formula here. Without using calculator or without any single formula, you solve the entire process. That is the advantage of this separation process. That's a graphical solution for this thermodynamic process. Even Mollier chart also you enjoyed for this drawing vertical lines for isentropic expansion in a turbine, and also the enthalpy is constant is some horizontal lines. Easily you solve the problems in using Mollier charts. Similarly here also you can go for this graphical solution, or there is another option is also is there. As I showed these tables, properties of the tables, you may use the tables and pick the properties and solve accordingly. I will show one here. From the property table, it's showing H2 is equal to 334, H3 is equal to 1638. After that, after the saturated liquid and saturated vapor, the mixer has been calculated 1 minus dryness fraction into H2, that's liquid HL, plus dryness fraction into HV, that gives 725.2 kilojoules per kg. Can be read directly from the chart also. Maybe let me see the difference. Okay, 770 is the solution here. 52 725 k. Because this is the approximate solution 770, but what are the for this analytical solution gives an exact value. Okay, you also may get some deviations if you are using the graphs, because exactly we can't read even though you are drawing the horizontal line, scale, pencil, exactly may be difficult because there small deviation will come. And also this is a chart. If the chart is big size, it's fine. A4 size means you will get more error. If possible, I won't restrict you. If it is A4 size is fine, means you may solve according to the A4 size. But if you have the facility, printing facility at Xerox shop, maybe slightly more than A4 size, that means A3 size also they can do, I think so. If you are asking your print, that's printing means the Xerox pupil, they may enlarge into A3, so that you can't get much error if you are using A3 size. Even A4 size also no issue, because I won't restrict to this COVID effect. I don't like to give you trouble, go and take the Xerox copy or outside. As per your convenience to take even A4 size also, it's fine. Okay, I'm stopping. I will continue in the next class. Do you have any questions in the solutions separation process? No.